Our project is the Tailings Dam Remediation project. Our site is located in the small mining town of Globe, Miami, Arizona, home to several tailings storage facilities. However, our focus was specifically on the Solid 2 tailings facility. The Solid 2 tailings facility is a legacy site which operated from 1928 to 1959 as a holding facility for copper tailings, with the tallest wall in the site standing at around 70 meters. As of date, this site approximately holds around 58.7 million cubic meters of tailings and has a surface area of 1.6 square kilometers. To put into perspective, that's about the size of 250 football fields.
When you are mining for something, like gold or copper, in order to obtain the profitable material, you have to dig up a lot of rock. Most of that rock isn't actually valuable. Typically, only a small portion contains the metals you are after. Afterward, this mined rock is crushed and processed to separate the valuable mineral from the rest. The remnants of this process is known as tailings. Tailings typically consist of a mixture of the fine sand, silts, and water. Tailings typically look like a muddy slurry. Something to note, too, that even though most of the valuable metals have been extracted, tailings can still contain trace amounts of that mineral. Because of this, tailings need to be carefully managed. Most mining operations store tailings in large containment areas, known as tailings storage facilities, or TSFs. These sites are designed to safely contain tailings and prevent it from causing harm to the environment or having any irreparable downstream consequences.
The reality is that many mining operations produce a lot of tailings, sometimes a lot more than actual valuable material. Over the life of a mine, this can add up to millions of tons of tailings. However, tailings can't just be dumped or left exposed, as if they aren't properly managed, they can have detrimental effects on local environments and communities. Tailings often contain fine particles and traces of chemicals that were utilized during processing. If left exposed, wind can blow these fine particles into the air, and rain can wash contaminants into nearby rivers, groundwater, and local ecosystems, all of which can impact air quality, human health, and surrounding environments.
It is important to understand that mining doesn't just involve extracting valuable materials, it also involves managing what was left behind. As we know, every mining operation generates a large amount of waste, and how that material is handled plays a critical role in protecting both people and the environment. In some cases, especially at older or inactive sites, waste hasn't always been managed to the standards we use today. Over time, this can lead to environmental and structural concerns that need to be addressed. In the past, we didn't fully understand the long-term environmental or social impacts tailings facilities can have, and in many cases, tailings were stored without the level of design, monitoring, or containment standards required today. So because of this, companies like to go back to these sites years later to carry out remediation. Like many older sites, the Solid 2 tailings facility was originally designed under the standards and knowledge available then, at the time. As engineering practices and safety criteria have evolved, however, it became clear that the facility did not meet the current factor of safety expectations. In addition, the presence of important infrastructure downstream, such as the hospital and school, meant that the potential consequences of a failure could be significant if something were to go wrong. Because of this, the focus became not on what was done in the past, but on how to bring the site up to current expectations and reduce risks going forward.
We were given a data package from our sponsor, BHP Copper, containing records of cone penetration tests, or CPT, sonic drill hole logs, and piezometer readings for the facility, along with the material properties of the tailings and underlying bedrock. Using this data, we modeled 8 cross-sections spaced evenly along the embankment of the site in Rock Science Slide 2. Using these models, our team was able to describe the laying of the tailings within the facility and assess its structural stability both before and after remediation. Modeling was a difficult task at first. There were relatively few drill hole and CPT logs considering the size of this facility, and the line between coarse and fine tailings was not cleanly defined. It was clear that modeling each section would require a bit of interpretation. To keep things consistent, we outlined a system for prioritizing different factors when modeling. We first checked lithology from the drill hole logs for clearly defined layers of material, and from there used moisture content and resistance measured by the CPT to differentiate between the saturated fine tailings and the unsaturated coarse tailings. Once each of the cross sections had been created, we performed a linear by elevation interpolation on the piezometer data in order to model the pore pressure within the facility.
The stability of the dam was quantified using a factor of safety, which is essentially a ratio of the weights of material to the ability of the structure to support that weight. When the factor of safety falls below 1 for a slice of the dam, then the dam will fail along the surface of that slice. Our team had ran a failure analysis in Slide 2 across 3 different scenarios. The first scenario considered the facility under standard conditions. However, due to the risk classification of the sites according to the Global Industry Standard on Tailings Management, We also had to account for a 1 in 10,000 year seismic event and a maximum probable precipitation event. For each scenario, thousands of potential failure surfaces were generated. The factors of safety under standard conditions were close to, but still above 1, which was expected for the site. We had determined earlier on that a critical failure was most likely to occur during the 1 in 10,000 year seismic event. So we examined surfaces for that scenario with a factor of safety lower than 1 and chose the critical failure surface for each section based on which would produce the largest failure.
Closely following industry standards, we began designing a buttress for the face of the facility. This would help with instability issues across the most vulnerable areas of the site, bringing it up to modern engineering standards. By using multiple layers of locally sourced materials, we were able to increase the factor of safety dramatically, keeping the budget relatively low and abiding by global and local standards while doing so. The first layer, located near the toe of the facility, is the drainage blanket. This layer helps the site deal with high rainfall events, which have historically been devastating for the community of Globe, Miami. The next layer is a rockfill layer, which adds weight to the face of the dam, increasing the factor of safety drastically. This layer is the largest layer and is the main stabilizing factor of the dam. Last but not least is the rock armor layer, covering the rockfill and acting as erosion protection for the rest of the dam. This section is designed to be exposed to rainfall, winds, and anything else that nature could throw at it, while still protecting the important stabilizing layers below. The overall cost estimation for our remediation efforts may seem high. However, it is important to keep in mind the danger these facilities can pose when not properly maintained. With our design, we can guarantee the safety of the community, workers, and environment. Tailings dams are designed to withstand extreme events, including major storm events and seismic loading. At this site, we consider both intense rainfall and earthquake scenarios that can impact stability. One of the key failure mechanisms under seismic loading is liquefaction. In this demonstration, we simulate the process using sand and water to show how shaking can cause liquefaction and upward movement of pore water. Liquefaction occurs when saturated materials, like tailings or loose sands, lose strength during shaking. As the ground moves, the particles rearrange and compress, increasing pore water pressure. Because the water cannot escape quickly, pressure builds up, and the material temporarily behaves more like a fluid than a solid. This loss of strength can lead to deformation or failure of the structure.
With our multi-layered buttress design, we were able to dramatically improve the factor of safety, meeting global and local requirements for stability. This ensures the safety of both the local community, environment, and reputation of our sponsor, BHP Copper. Thank you for watching.